Linear algebra is a really big discipline within mathematics. And so it's just impossible to include everything about linear algebra in one book. And so I had to pick and choose which topics in linear algebra I wanted to include in this book. And obviously, as you can imagine, I chose to include the aspects of linear algebra that are most relevant for applications in data science, statistics, machine learning, deep learning, and these kinds of technical data related fields. So there's a lot of interesting, sometimes quirky things about linear algebra that are maybe interesting, but not so relevant. And so I do want to have a little bit of a smattering of these kind of interesting things throughout the book. Um, and that kind of inspired me to come up with this exercise here, exercise 3 of chapter 10. Now, this is actually focused on LU decomposition and the determinant of a matrix. Now, you know that the determinant of a matrix is a quantity that is very difficult to calculate with high accuracy. I've had lots of discussions and exercises about that in the book. So that's why I don't really talk a whole lot about the determinant in this book in terms of applications. But so this exercise is focused on two little factoids about the determinant. One is that the determinant of a triangular matrix equals the product of the diagonals. So if you have a triangular matrix, instead of going through a really complicated formula to compute the determinant, you can simply take the diagonals and multiply them, and that gives you the determinant of a matrix. Furthermore, the determinant of a product matrix is the product of the two determinants. So the determinant of A times B equals the determinant of A times the determinant of B. Okay, and then I write, putting these two facts together, you can compute the determinant of a matrix as the product of the diagonals of L times the product of the diagonals of U. So you take the LU decomposition. Now, I've discussed this just in the previous video, and I also wrote about this in this chapter, that the diagonals of the L matrix are all 1. And so 1 times 1 times 1 times 1 times 1, or however many elements there are in U, in the diagonal of U, it's all going to be 1. Okay, so this means that we can compute the determinant of a matrix, A, as the product of the diagonals of U. So with that in mind, with that as background, what I want you to do in Python is construct a matrix and then take its LU decomposition and compute the product of the diagonals of U, and then compare that to the result of numpy.linalg.det for determinant, the linear algebra module function for computing the determinant. And then repeat it multiple times for different random matrices, and then I say, before reading the next paragraph. So there is more to this exercise, but first I'm going to switch to Python, show you this code, and have a bit of a discussion about it, and then we'll come back to the rest of this exercise in the book. So here I construct a 6 by 6 random numbers matrix. I take its LU decomposition, and now notice I'm just taking the product of the diagonal elements of U. I'm not doing anything with L, and just multiply all the diagonal elements of U together. And here I'm comparing that against the determinant from NumPy. So that's just numpy.linalg.det. Here I print them both out next to each other, and here I subtract them. Of course, if these are equal, the difference between them should be 0. So let's run this code, and here we get 16.037. Here we get here is plus 16.037. So of course the difference between them is minus 32. So that's pretty weird. Let's try this again. Okay, so here we get 17.8, 17.8, and the difference is 0. Now, we cannot make any predictions for what the determinant will be because these are just random matrices, but we do expect these two to be the same, whatever the determinant has to be. And what you can see is that sometimes they are the same. This is 0, rounding error. Sometimes they are the same, and sometimes they look the same, so they're the same magnitude, but they're opposite sign. So what is going on there? So according to the book, written by someone who clearly knows something about linear algebra, this author assumes that we found that the determinants match in magnitude, but the signs would seemingly randomly differ. That is indeed what I found, and I believe you found the same thing. Why did that happen? Okay, this happened because I omitted the permutation matrix in the instructions. And the determinant of a permutation matrix is either +1 or -1, depending on how many swaps there are. So +1 for an even number of row swaps, -1 for an odd number of row swaps. Okay, so now we go back to the code and include the determinant of p in your computations. So where do we include this? Well, the idea is that the determinant of A is equal to the determinant of P times the determinant of U times the determinant of, L times the determinant of U. So basically the products of the determinants of these three matrices. Now, we know that the determinant of U is the product of the diagonals. Again, I haven't proven that, I've just stated it. That's because, I just didn't take the time to discuss it in this book. So we know that the determinant of U is this term here. The determinant of L is 1 because that's also a diagonal matrix. So the determinant of a diagonal matrix, a triangular matrix, is the product of its diagonals, but we know that those are all 1. Okay, so what we need to do here is multiply by the determinant of P, like this. And we know that this is going to be +1 or -1, depending on the number of row swaps in LU decomposition. And that's basically random because these are random. It's random in the sense that I cannot predict a priori whether the determinant is going to be +1 or -1 because these are random numbers. Okay, so then when we include that, now you will see that we don't get any errors. So the magnitudes match and the signs match over and over and over again. No matter how many times I run this, okay, sometimes you get these little rounding errors, but it's always basically 0.